All right, the practical video on working with Clausius-Clapeyron equation. So, few things on this equation. First of all, pressure terms. Here, the units don't matter. And the reason the units don't matter is that we can't take the natural log of units. So the only rule here is that P2 over P1, both pressures have to have the same unit. So we can work in millimeters of mercury, we can work in torr, we can work in kPa, atmospheres, it doesn't matter. And again, the reason it doesn't matter is that those units are going to cancel out. And if you work it out, it's really the ratio of the pressures. Any pressures you convert it to will give you the exact same pressures. Temperatures. Automatically, you should know that this is in Kelvin because once you see the ideal gas constant, you are automatically working in units of temperature. Temperatures are automatically working in units of Kelvin. So temperature here has to be converted to Kelvin, and this is one of the most common mistakes I see when people work with. Now, how about R? Well, this is where you're going to see the chemists and the engineers fight with each other, and I know I'm a little biased. The engineers are right here. Do not work with 8.314. No one reports delta H in terms of joules per mole Kelvin. Go look up any thermodynamic database. NIST, GenF, they're all in kilojoules. So what you should be working with for R is 0.008314 kilojoules mole Kelvin. This is the correct value of R, and it is the correct value of R because delta H is typically reported in terms of kilojoules per mole. Now, how about this delta H of vaporization? The heat of vaporization is the heat of the gas phase minus the heat of whatever phase you came from, either being a liquid or a solid. So intuit to yourself, who has more heat? The gas phase or the liquid or solid phase? And hopefully you can see that we have to heat a liquid to make a gas. So automatically the gas is going to have more heat than the liquid or solid phase. So we get this condition that the delta H of vaporization here is always greater than 0. We don't automatically get a phase change. We have to supply heat to a liquid in order to get it to go through a phase change. Now a reasonable range for this, 25 to 150 kilojoules per mole. Now, is that a hard and fast limit? No. Some boil less than that, some boil, something like naphthalene is going to take hundreds of thousands. Like, it's going to take a lot of energy to boil something really heavy. But for most practical things that are liquids at room temperatures, 25 to 150 is a very reasonable range. So, that should be a positive number. Units here don't matter. 0.008314 kilojoules per mole Kelvin. And temperature needs to be worked with in terms of Kelvin. What do you do? What's some diagnostic issues you might have? Well, first of all, think about it this way. What happens to vapor pressure? The pressure is we increase the temperature. It should go up, right? So as you're working these problems, if you're given two pressures and you're asked to solve for a temperature, intuit to yourself, the higher pressure should have the higher temperature. Or if you're given both temperatures and asked to find a pressure, the higher temperature should correspond to the higher pressure. These P1s and P2s are also arbitrary assignments if you really look at the bounds of integration. We can always integrate backwards, it's just a negative sign. So if you want to, however you define them, the only rule here is that this temperature has to correspond to this pressure and this temperature has to correspond to this pressure. So if it's easier, if your unknown variable is P2 and you're given another pressure, just define this is pressure 1, the one you know, and just correspond to the correct temperature. Now, if you get a negative delta H of vaporization, 99% of the time, I guarantee you, it's because you flip P2, P1, or you flip T1, T2. You know the delta H of vaporization should be positive, so you probably just drop the negative sign somewhere, or you flip something. So this is the practical side of working Clausius-Clapeyron. The only way to truly make these problems difficult, okay, two ways. First is to make you solve for temperature. And the reason that's hard is just because it's an inverse relationship. So if you're asked to solve for temperature, let's say in this case T1, you're going to have to do some rearrangements. So you get R, ln, P2 over P1, over delta H of vaporization, plus 1 over T2 equals 1 over T1. Please go work the algebra on your own. What makes it hard is you're doing algebraic manipulations. The other way to make these hard is to make you find pressure, and honestly, if you're familiar with logs, this should be pretty straightforward. P2 over P1 is just E to all of this mess. And then we can solve for P2 or P1. Now again, because the assignments for P1 and P2 are arbitrary in this equation, feel free to assign them to whatever you want. If you're solving for an unknown pressure, it's best to define that unknown pressure. Ooh, sorry about that. As P2. And just make sure that the temperature corresponding to that unknown pressure is T2 in your equation. So this is working with Clasius-Clapeyron. And if you want to see a video on how it's derived, I have another video up on it. But these are the practical considerations when trying to be quantitative with this equation.